All right, so in this particular talk, we are going to talk the very, very beginnings of how to build a bytecode virtual machine. That is to say, if you were ever interested in how virtual machines like the Java virtual machine, the CLR over in the .NET world, the Python VM, the Ruby VM, Erlang, all of these virtual machines operate in very, very similar ways. And one of the best ways to learn a thing is to try to build a thing, okay? Now, if your interpretation of the title was that I was going to show you how to create a virtual machine using something like VMware or VirtualBox, yeah, no, that's not at all what we're going to do here. This is not a DevOps talk around, one of those things. This is literally how you do file new project and begin building. Now, in the interest of transparency, normally this is a full day workshop. Right, so this is going to be an overview of the steps that one would take towards building this. There is a commensurate GitHub project over here that I will be coming to periodically to show you some code. And this would be, if you fork this, there's a whole bunch of different branches that describe exactly what it is you're going to do at each particular step, right? So you would check out step 0, begin. And the instructions for what we do during this particular step are listed here. So you could, if you so choose, you could certainly do the workshop yourself at home on your own time. For every begin, there's a corresponding end, which has my implementation, which is what I'll be showing as part of the code part of this. But I do strongly encourage that if you're interested in virtual machines, and frankly, if you're not interested in virtual machines, I don't know why the hell you would stay here. It's interesting and informative, and quite honestly, it's a little fun to sit here and build your own. Okay. Now, from a pragmatic perspective, are you going to build something in a couple of days that rivals the Java virtual machine? No. Okay, just no. You're not. There are so many person hours that have gone into the implementation of the JVM. You as a lone individual will never get to the point where you have something that is as intricate, as powerful, as optimized as the JVM or the CLR or the Python VM. However, don't discount the idea of building your own VM entirely as part of production work, because one of the things you begin to see is when you see the bytecode laid out in front of you and when you start diving into certain research, around this area, you start to realize that really you could do anything you want in terms of bytecode, and bytecode is a, assembly-like thing that could be in fact expressed in various different language constructs, etc. One of the most interesting and eye-opening moments for me personally was when I was looking at some of the action script of, you remember the Flash days, right? Before Apple killed that off because it was so terrible, which it actually wasn't, but Steve Jobs, that's what he does. He kills things off, right? ActionScript actually had some built-in primitives in their virtual machine for working with multimedia constructs. Like literally there was primitives in the virtual machine for being able to load and play a video, or for being able to load and play sound. Not all of the virtual machines have to look exactly like the JVM does. And in fact, a number of game engines are built around some of these same kinds of principles, with the idea that we're going to create a core and then other people are going to build things that help drive that core. And frankly, that can be a very, very powerful mechanism if you're looking for ways to create some extensibility in the business applications that you're working on. If the marketing folks want to keep changing things periodically, you could literally build a DSL that transpiles into bytecode that is interpreted by your machine that then, calculates marketing promotions, whatever, right? Whatever it is the marketing folks can dream up, you could build something that actually makes it somewhat self-service. So learning to build one of these guys is simultaneously an exercise in understanding one level below the level at which you work. That is to say, when you write Java code or you write Python or Ruby or whatever, understanding what it transforms into and how that operates. But it also has some practical purposes as well, in that it creates extensibility points for other folks. So Yeah, let's build one. So how exactly do we start with this? Well, it begins with a definition. What do we mean when we say virtual machine? An abstraction that defines a computing model, aka abstract machine, right? When you look at the JVM, you look at the CLR, they fundamentally behave, they look similar to a CPU/hardware model because it's a relatively easy model to understand, and we often want these things to behave in ways similar to a CPU without being tied to specific hardware. But it is, by every notion, it is an abstraction of. There's really not a whole lot of point in creating a virtual machine that uses x86 code because we could just do that directly to the CPU. We often want to simplify and in many cases provide some additional guarantees around what this virtual machine does. What does it provide? Well, typically the virtual machine provides a bunch of stuff to support state, that is to say data. Where this data lives can in fact be a couple of different places. We usually have 3 different kinds of explicit places to put state. There's generally some form of static state. This is, for example, if I declare a static variable in Java, the static space is where those guys go and live. You can think of it principally as global storage, if you like, inside of your virtual machine. There's also typically stack space. When we start getting into being able to call functions and procedures and so forth, we find it very helpful to be able to push parameters onto a stack and then pop that stack in order to be able to do very, very quick cleanup for that particular procedure call. So we typically have some form of operand stack. And then we typically have some sort of dynamically allocated space. And in the JVM, for example, every time you say new X, that's allocating space out of that dynamic space. So a VM will typically provide all 3 of these different kinds of storage. There's also often some implicit state that's in various places. So for example, when the JVM allocates memory to hold your class in memory, go through the whole class loader thing, we do the verifier. Now that class needs to live somewhere in memory because JVM needs to understand what this thing is. It needs to understand how big it is, how many fields, what the name of the fields are, what the names of the methods are. All of that needs to be stored somewhere inside of the JVM. The JVM historically actually had a separate dynamic space to put all of that. And then circa Java 6, Java 7, I don't remember exactly when, they realized that that was creating problems because now they had basically 2 separate garbage collectors running. And the class space was always potentially running out of space. And they said, why not just put it into the same place that all of the other dynamically allocated objects live, right? We also have code. That's a large part of what we're trying to do here is execute code. So a virtual machine also has to be able to execute the various things that we want to do. Now, typically for a virtual machine, this will be some form of bytecode. It is possible to build a virtual machine that uses native instructions, but now again, we're kind of defeating the whole point of an abstraction over hardware. Part of the advantage the JVM has, that the CLR has, etc., is they can at runtime take a look at the kind of hardware they're running on and optimize the native instructions that they generate based on the actual hardware that's underneath. Anybody here old enough to remember writing C++ code? Oh, wow. There's a lot of you out there. You guys remember having to throw all those optimization switches? Right? Wasn't that fun? Trying to decide ahead of time what the CPU would be that it would run on and always being wrong. Right? Because, I mean, it kind of got to a point where you'd say, okay, let's assume that they're running on top of a 386, but if they're running on a Pentium, there's all these really cool optimizations that would make the code go faster. But if it happened to be like given to somebody who was going to be running a 286, the code wouldn't even run because certain execution instructions the CPU would just be like, I have no idea what to do with this, and crash the program. And meanwhile, the Gen Zers in the crowd are like, what's a Pentium? Why do I care? Because this is a beautiful thing about a virtual machine. It doesn't care what the hardware is. It'll either stay in fully interpreted mode, or it knows this particular CPU and knows how to generate native instructions for that particular CPU, okay? Now, typically that means we also have to define some mechanisms for being able to load and resolve this code, right? Loading simply means getting it off of disk or over the network or from the database or wherever this code happens to live. Resolution is typically the step of trying to turn it into that in-memory data structure that the virtual machine understands and knows how to begin to execute. And occasionally we start doing some manipulation on stuff. If you ever did any of the Java aspect-oriented stuff at runtime, that's exactly what that bytecode weaving is reminiscent of. VM typically provides a number of libraries as well, standard library, and also provides a certain amount of services, such as automatic memory management. I will not be talking about how to build a garbage collector in this talk. That is an entirely different discussion, and the virtual machine that we're going to build is not going to get anywhere close to that level of sophistication. But it will often be the kind of thing that you would want a real-world virtual machine to do. And quite frankly, would also like it to have some amount of metadata, right? So when you load some code, being able to examine that code at runtime and potentially change it, right? This is one of the things that the Python virtual machine allows us to do, is to load a class or to define a class entirely at runtime and then be able to manipulate it in various ways. JavaScript is also very popular for knowing how to do some of this stuff. Typically, you'll also want to have some sort of host-guest interaction, which is often known as an FFI, or foreign function interface, right? This is one of the things that Java has tried very hard to fix more recently, because the JNI API was really something that not even a mother could love. So let's talk about some of the major moving parts. There's a loader and dynamic linker. This is what's responsible for taking the file off of disk and bringing it into memory. There's the execution engine. This is the heart, and this is going to be the thing that we're going to focus on the most in this particular discussion, where we essentially go through a fetch, decode, execute mechanism. If you go all the way back to Java 1.0, and even when you look at Java 23 today, somewhere inside there is a really big loop that says, I'm going to grab a bytecode off of disk or out of memory, wherever this thing happens to be stored, and I'm going to figure out if there are any operands that need to go with this, and then I'm going to execute that, and then I'm going to continue to loop until I run out of bytecode. That is the heart of what any virtual machine does. Memory manager, if your machine supports the idea of threads, there may be a thread scheduler, whether those are real threads like what Java did in the early days before we had Project Bloom and virtual threads and so forth. Sometimes the non-real threads are known as coroutines or fibers, or there's a variety of different things. So thread here doesn't necessarily mean hard operating system level thread. Again, this is an abstraction, and we can in fact play with some assumptions that programmers make. For example, one of the reasons lots of people like the Erlang virtual machine is when they talk about spinning up a process, they're talking about spinning up essentially one of these fetch execute cycles, which is actually very lightweight. So an Erlang program can have literally tens of thousands of these things running simultaneously. They are actor models, sending and receiving messages, but the virtual machine maps them to underlying hard threads as necessary, and the programmer is essentially left blissfully ignorant as to whether or not there is a hard thread here, or did we switch threads. This is a large part of what Project Loom is trying to get us to as developers in the Java space. All right, typically there's the bytecode is its own unique instruction set architecture, ISA, loaded from disk. The format is often optimized for the virtual machine's purposes. In many cases, it will be optimized, if it can be, for programmer purposes. In the case where you're building one for yourself, you're probably going to optimize it for ease of implementation, which is, a good thing when you're just getting started building something. Most of them will have some form of instruction pointer or program counter. This is literally, where am I in the code? Now, on a CPU, this is a register that holds this value. In a virtual machine, this will be essentially an int, or if a 32-bit value is not large enough for you because you are actually anticipating having more than 2 to 32 bytecode instructions, you could make this a 64-bit value. Again, this is up to you as the bytecode, as the virtual machine implementers. This is your choice. But one of the things we're going to discover very quickly is that all of the bytecode operations, they influence this. Every time you do an if-else, this is essentially a program counter adjustment. Typically, the virtual machine will have a call stack of some form. Now, in some cases, the virtual machine will actually try to use the native call stack, right? The JVM will actually do this. But for the advantage of that, which is to say it makes it easier to be able to do native code execution, there's also disadvantages because periodically, for example, the Java virtual machine needs to walk that call stack. The most obvious case is, of course, when an exception is generated, it needs to walk the call stack in order to be able to have that call stack to be able to display to you. As a virtual machine implementer, you get the choice of whether or not this call stack mirrors the native code call stack or whether it's your own data structure that you choose to manipulate. And for a beginning virtual machine, it's usually much easier to have this as its own data structure. The stack consisting of each of these different call frames that contain information about that particular function call. Most notably, parameters to the function and or local variables that are declared there. There is a frame pointer or stack pointer, or sometimes actually both. In a virtual machine that uses the native stack, the frame pointer and the stack pointer will often be the same. If you have a separate execution stack from your call frame stack, then these would be two separate values that you're walking through. Both of them serve the same purpose as the IP, to simply say this is where we are right now. There's typically some global memory, which, surprise, it's basically an array. It's going to be typically have some form of addressing scheme. Again, if we talk about something that's heavily optimized like the Java virtual machine, this will actually be process memory. If we talk about something that's more abstracted, this may very well be like an array of integers, which is what we're going to use in the implementation later. The heap, this is dynamic allocation. This, again, is an array of cells. Because remember, memory is basically indexed array of cells. It's just slots. It's places we put stuff. The processor, this is the software CPU. This is often either a class or a series of methods inside of the virtual machine, but this is what does the actual CPU execution, that fetch, decode, execute cycle. By the way, you'll notice that it's constantly fetch, decode, execute. But when we start looking at the code that I'm writing, you're going to discover there's no decode method. Part of this is because when people start building these bytecode, they often want to try to optimize and get the maximum number of instructions in the smallest possible space. So there will often be a certain amount of bit masking that takes place. Like the first 3 bits will be what kind of instruction it is. The second couple of bits will be what register it operates on. The third couple of bits might be whether or not it's loading a constant, etc. For a simple virtual machine, look, just make them integer constants and be happy with your life. You don't really need to be doing a whole lot of decoding, particularly because in the implementation that I've got here, there's maybe like 24 bytecode instructions, period. But if you start getting to trying to get something that's more production ready, if you look, for example, at the Dalvik virtual machine, which was the VM that used to run on Android, they do a large amount of this bit packing. And so it helps to do an explicit decode step to unpack the various bits in that 32-bit value to understand what it is we're executing. Now, constants are kind of a fun thing. In some virtual machines, like the Java virtual machine or the CLR, we actually find that constants show up repeatedly. And the virtual machine designers said, you know, that feels like it could be potentially a waste of space. If we constantly have the same string somewhere, And by the way, these strings may not just be the strings that the programmers introduce. These will also be the strings like names of classes, names of methods, names of fields. All of these are constants. It might actually help save some space if we put them all in one place, aka the constant pool or the constant table. The JVM calls it a constant pool. The CLR refers to them as a constants table because the CLR actually stores everything in small relational tables inside of the exe that is produced. Again, for a beginning virtual machine, that level of indirection may be a little bit overcomplicated. So for my implementation, I just choose to let constants remain where they are inside of the bytecode. But this is one of the places where, as a virtual machine implementer, your mileage may vary. You may actually prefer to see those constants stored in one place, in which case we will typically put all of the constants in that one place. And then anytime we want to reference one of those constants, we will always do so by index into that pool. As far as the bytecode itself, what are we typically looking at? Well, these are generally, as much as we call it bytecode, they actually tend to be larger than single bytes. So for example, in the one that I'm building, I'm just using 32-bit integers, right? If we look at some of the production level virtual machine stuff, the Java virtual machine, it is a byte, but it is a heavily packed byte. And they actually have a number of specifics depending upon the kinds of types that they're working with. What you will notice, particularly as we go through some of this, is that it is extraordinarily low level. It's tied very directly to the virtual machine itself. So it doesn't make sense, for example, to try to take the Java virtual machine bytecode set and try to apply it directly to using things on hardware. There's got to be some kind of level of translation there. And again, that's what your JIT compiler does. One of the things down here at the bottom, though, you'll notice I say stack versus register machine. One of the key things that you will decide when you get started building a virtual machine is, do you want to build a stack-based machine, aka what the JVM has, or would you want to do something that has a large number of registers available to it, which is actually more similar to what we see with some of the more modern hardware. The x86 CPU was actually heavily disliked by a lot of compiler implementers for many, many years because it has a very, very small set of registers, right? It basically had 8 registers that you could do anything with, 4 of which generally were very, very specific purpose and you couldn't use for anything else. And therefore, a stack-based virtual machine made a lot more sense when trying to implement this on top of that platform. If you went to a CPU that had more registers, well, okay, cool. Instead of pushing something onto the stack, we could always shove it into a register and the programmer doesn't know or care. But the perception from the developer's perspective was always stack-based. Both the JVM and the CLR are both stack-based virtual machines. There have been experiments with doing some register-based virtual machines, most notably Parrot, which was a VM that was created by the folks who did Perl. By the way, did you know that we recently celebrated the 20th anniversary of Perl 5's announcement? We didn't celebrate it. That's a good point. We kind of celebrated the fact that Perl is dead, but Gregor Hopia, everybody. Anyway. So these tend to be very low-level decisions. Stack machines are generally more popular than register-based machines. Again, that's usually because they're a little bit simpler to understand and reason about, but we'll talk a little bit about both. Within bytecode, you typically see a variety of different categories. We can manipulate the stack, do the arithmetic operations, flow control, storage. Depending upon your machine, if you have some measure of type safety, we'll often need to do some kind of type conversion. I'll need to take an integer and convert it to a long, etc. There are about a dozen or so bytecode in the JVM, for example, that deal specifically with moving between these different kinds of constant types. Okay? So now we start getting to some of the higher level invocations, and this is where things get kind of fun. Because most machines will all do all of the previous page in terms of what operations are there. But now, depending upon your virtual machine, you may exactly choose to offer some different higher level semantics. For example, Smalltalk virtual machines had baked into them the idea of being able to send a message from one object to another. That was the foundation of how Smalltalk did a good chunk of its object orientation. And as a matter of fact, this is what Alan Kay was referring to when he said, I invented the term object-oriented, and I can tell you C++ was not what I had in mind. What he was referring to was not the C++'s syntax, but the fact that C++ was doing C-style function invocation rather than sending messages back and forth. Smalltalk virtual machines implement the notion of sending a message as a bytecode primitive, as opposed to doing a method call. In other virtual machines, we may actually have the ability to define a closure, an anonymous block of code, as a single bytecode implementation, because that's what functional languages do on a regular basis. As a bytecode implementer, you are free to take anything under the sun and make it into a bytecode and make it an atomic operation of your particular virtual machine. Now, all of this, with the exception of the first one, all of this is really beyond the scope of what you can do in like a given day for building a virtual machine. Typically, opcodes are made of two parts, code and some parameters. There may actually be some other things that are around it, labels, directives. This will typically be more at an assembler level, a tool that will be used to help turn the bytecode into something. But let's actually start by looking at some code. Just out of curiosity, how many people in here write Java on a regular basis? Anybody in here write C# on a regular basis? Okay, we'll look at the Java implementation. Sorry, C-sharpers, you're just gonna have to live with it. All right, so one of the first things that we do is we generally want to define, whoops, not begin, I want end. There we go. All right, so one of the things we typically want to do is we want to start by defining some of our bytecode, right? For this particular step, we're doing some fairly basic things. We're just getting some core infrastructure in place. So we have some basic bytecode instructions, which are almost always the starting place. For example, everybody's favorite no-op, okay? The no-op instruction is basically the teenager instruction. Do nothing, okay? Now, the no-op instruction actually turns out to be way more important than you might think because it often serves as a placeholder. Frequently, when a compiler is looking at, for example, trying to predict, okay, here is an if statement, and there's a corresponding else statement, so I know we're going to have to branch to some place, so let me lay down a whole bunch of no-op instructions as a placeholder, because I can then start writing the actual instructions on top of those no-ops, and therefore I know that there is space there allocated, but I can replace the no-ops, and even if we start executing no-ops, these are typically optimized away anyway. So they're a very, very useful placeholder. If, for example, you start working with debuggers, debuggers will often set up breakpoints by replacing a no-op with a break opcode. That is one thing that is missing here, is I don't have any sort of debug break opcodes, which is actually something that a virtual machine very commonly provides to notify any sort of attached debugger that, yeah, you should actually, we're going to stop execution and you should grab some data and display it to the debugger. You can also see that I have several opcodes here that are very specific to my personal implementation needs: a trace, a dump, and a print. Print is simply to give me some information about my running virtual machine. Dump is actually print is to give me information of what's on the top of the stack. This is literally like your print call. Dump is what gives me information about the state of the virtual machine. And trace turns a trace flag on or off inside of the virtual machine so I can see what's going on. And my virtual machine, you notice I create my own specific exception type just because. Here is my trace flag to let me know whether or not we are tracing. And all I'm doing here is I'm simply saying, if trace is on, we're at this instruction pointer, and this is whatever it is I want to trace out. You'll notice my dump is very simple because all I really have in terms of my implementation so far is I'm going to have an instruction pointer and I'm going to have a working stack. Again, stack machines are a little bit easier to work with, so I begin using that. And you'll notice my stack pointer here begins at -1 because, of course, C always chooses to let 0 be the start of an array. So SP-1 means that currently I have nothing on the stack, period. And you'll notice I've got some internal implementation methods here to push things onto the stack and or to pop things off the stack. This right here, by the way, is the heart of what this virtual machine is going to be doing on a regular basis. So in order to make sure that I've got all this prefix increment, postfix decrement, all of that stuff, to make sure I've got all that working, it is often very useful to create a series of tests. Okay? So these tests over here simply test that if I push something onto the stack, I know that the stack is 1 in length. I know that the first element on the stack is that value that I pushed. If I pop it off, the stack should no longer have any length to it. And the value that was popped is, in fact, that which was pushed earlier. When you're building a virtual machine, one of the most beautiful things it is just naturally lending itself well to tests because you are literally running bytecode through it and your VM should be deterministic. Should be. Unless for some reason you really want to build one that isn't. So this is our basic infrastructure for our virtual machine, okay? Now, if we go a little bit further down, you'll notice that I have execute here that takes an opcode and a variable list of operands, but further down, we actually have execute taking an integer array. This is actually the closest I'm going to get to a decode step. So the idea is that certain opcodes do not take any operands out of the bytecode stream. Keep in mind that bytecodes are going to have a couple of different places to pull their parameters. One is they're going to pull it from the bytecode stream itself. So if I, for example, push a constant value onto the stack, the next value in the bytecode stream is the value that I want to push. But for no-op, trace, dump, print, fatal, and pop, they don't take any parameters. Pop will say, let me take whatever's at the top of the stack and pop it off, whereas const is going to push it onto the stack. Now, again, some people will say, well, why do you have it const versus pop? Shouldn't it be push and pop? Name your bytecode whatever you want. To me, it makes more sense that I am pushing a constant value on the stack as opposed to pushing a value onto the stack. But honestly, if you are loading a constant out of the constant pool, the JVM uses the acronym LDC, as in load from constant pool and push that onto the stack. For a stack-based virtual machine, everything will be done in terms of this stack. Just out of curiosity, how many of you have ever looked at the bytecode that is created by the Java-C compiler? Using like the Java P utility and so forth. Okay, if you've done that, then you've probably seen these execution instructions very, very similarly. If you've not, I strongly encourage you to take hello world, Java-C hello world, then run the utility Java P on the bytecode, Java P C verbose, that is Java P-C -verbose, on the corresponding class file. And you will see the constant pool, you will see the instructions, you will see how they will in fact load a constant out of the constant pool and push it onto the stack. All of this will look very familiar when you start looking at the Java P instructions. And yeah, right now I have all of these that take no operands, just this one that takes one operand. And, assuming my tests here, I mean, this is just basic stuff. These are tests to verify the stack. I do not promise that this has 100% code coverage, but I also don't promise that I'm ever going to ship this thing either. So the next step really starts to get to what sort of additional instructions can we support? Well, if we know how to push things onto the stack and pop them back off, the next most natural thing is to actually do math to them. Can I add these values together? Can I subtract values from one another, etc.? So from a bytecode perspective, let's see. I'm going to fast forward through some of this just to... So here we see push, pop. One of the common bytecode instructions is also duplicate, which is to pop a value off, but then push it on twice. You see this opcode all the time in the JVM because it's frequently saying, I want to take a value and I know I'm going to use it twice, usually as a parameter to an upcoming function call, right? So I'm going to dupe that top of stack value repeatedly, okay? Binary math operations, they typically take two operands. So from the perspective of a stack-based virtual machine, we are going to take the top two elements on the stack, add them together. We're going to pop them off the stack, add them together, and push the result onto the top of the stack. This is what we mean when we talk about a stack-based virtual machine. Everything happens in terms of that operand stack. So you can probably already guess what the code will look like when we look at the implementation of this guy. Let's go over to virtual machine here. So when we get to the add instruction, right, notice we pop those two, store them into locals, and then add the two together and push them back. Now, for the add instruction, we don't particularly care. But if I'm going to subtract 4 minus 2, the order of operands on the stack becomes really kind of important. Which one is subtracted from the other? Which is the left-hand side versus which is the right-hand side? This is a convention that as the implementer of the virtual machine, you're going to have to establish. And by the way, if you've ever heard the term C calling convention or Pascal calling convention, this is exactly what we're talking about. When we push parameters onto the stack, what order do we push them in? Do we push them in from sort of a left to right order? So the first parameter is the one that gets pushed furthest down the stack? Or do we do this in a right to left fashion, right? So that the right-hand parameter is the one that's furthest down the stack. You can choose whichever way you go, just make sure you're consistent. Now again, the programmer, the person who's building the language, the person who's writing the language code that gets turned into this bytecode, they're never going to see nor care about the difference. But at the bytecode / assembly level, this will be the kind of thing that you will need to decide. And this is part of the reason why the C calling convention has become so popular, is because this is a natural way that all of the C compilers in the world that did things, so that if you build your own virtual machine that wants to call out to native methods C style, well, you just follow the C calling convention style. And there are reasons for doing left to right versus right to left, and I won't get into all of them here, other than simply to say, I'm going to choose to do a left to right order, which means I want to extract in the reverse order. Okay? Now for add, it's not going to make a whole lot of difference because 2 plus 4, 4 plus 2, they all add up to 6. But for subtract, it's going to make a big amount of difference. Thank God for unit tests. Okay? You'll also notice though that mul and div and mod, they all look basically the same. The only thing that's different is the actual mathematical operation. There is a part of me that says, I really want to somehow refactor this and turn this into like one block of code where I then switch on the actual instruction. But at a virtual machine level, when you're doing thousands of these per second, it may actually be faster to unroll the code like this. Because then I don't have to do that additional switch. I just go to add, I pop, pop, add, push, as opposed to pop, pop, switch, then do the operation and then push. Because at a virtual machine level, we really do care all of a sudden about those extra additional execution instructions. Now again, I'm never going to take this thing to production. Could I get away with doing that to make the code ostensibly a little bit easier to read? Maybe, maybe not. This also has the advantage of being very clear and explicit at the cost of a slight amount of duplication. But it's only going to be a problem if I ever introduce new binary operators, which I don't really intend to do. So again, this is some of the trade-off that might go on in some of the design discussions. We also have a few unary math operations. If I want to take the absolute value of a value, if I want to negate a value, again, you can see we just do the same kind of thing. By the way, this is the most exciting, fun part of building a virtual machine, is actually deciding what your bytecode is going to do and then doing it. Okay? So if you're not really excited right now, really excited? Yay. Yay. Woo. I got a woohoo. We're moving on. All right. Couple other steps to go through here. So for example, the next would be actually, once we've started doing some mathematics operations, the next obvious thing is to be able to do some comparisons, right? Greater than, less than, greater than, equal to, etc., right? So here, for example, I have some tests that will push a couple of constant values and to ask, are they in fact equal? So 5 and 5, the equals operator, like the binary math operators, is going to pop the top two elements off the stack, compare them, and then push the result back onto the stack. What should the result be? Well, I mean, this is fundamentally a Boolean, but we don't have Booleans at the virtual machine level. All I have are these integer binary values. I have the words that we are working with inside the virtual machine. So typically, again, we establish the convention. 0 means false, 1 means true. Or if you're a Visual Basic programmer, 0 means true and -1 means false, because Visual Basic. Okay? You get to, again, make those decisions. So I don't even need to show you the implementation of these guys because they're basically going to look exactly like the math operations. It's just now they're going to do comparisons instead of actual addition, subtraction. And let's see, the other thing that we will often want to do after we compare is we'll want to do jumps. This is where things get fun from a bytecode level because now you really begin to appreciate what your compiler does for you on a regular basis. Because implementing the jump bytecode is basically a go-to. All you do is futz with the instruction pointer and continue execution. By the way, in the fetch, decode, execute loop, make sure that you don't increment the instruction pointer after doing a jump bytecode because now you've just thrown it off by 1. Again, thank God for unit tests. But notice here, if I want to jump to instruction 3, I actually have little comments here to help me keep track of what exactly instruction 3 is, because we start from 0. Notice the fatal instruction there. If the VM terminates using the fatal bytecode, this is useful for me to know because it shouldn't do that. You will often see in some assembled code, you will often see reference to doing things that will cause the program to crash to make sure that if we don't jump over this, we get a fail fast kind of response. Notice there's also an R jump here. This is a relative jump to whatever the current instruction pointer is, offset by a certain value, which could in fact be negative. This would be how we would jump to an earlier part in the bytecode stream. And so on, and so on. There is a jump indirect, meaning grab the top of the stack and jumped to that location, versus a relative jump indirect. And you start to see why, when we start combining, whether we jump relative to our current location or to an absolute location, whether we jump to a value that's coming from the bytecode stream or we pull it off the top of the stack, you start to see how the bytecode begins to multiply and turn into a variety of different instructions. There are more steps in this particular workshop, in this particular sequence of operations. We then start to get into things like manipulating global state, globals, being able to push things into global and fetch them back out. We then get into procedure calls, jump to a particular location in the code and begin executing. And by the way, here is a call frame structure that contains local values, et cetera, et cetera, et cetera. This is a 40-minute whirlwind tour. If any of this did not put you to sleep, you might be somebody who gets excited about investigating and playing around with virtual machines and doing some research. I encourage you to go grab, fork the VM-impl, the workshop VM-impl project off of GitHub. I encourage you to go search on GitHub for other virtual machine implementations. This could very well be the beginning of a lifelong obsession. You're welcome.